You know, there's this hidden world of high-stakes industrial repair all around us. We're talking about massive pressure vessels, sprawling pipelines, all the critical infrastructure that we rely on every single day. Stuff that absolutely cannot be allowed to fail. But what happens when one of those things needs a repair that seems, well, impossible?
And that's the million-dollar question, isn't it? This is a challenge engineers face all the time. A crack or a defect in a crucial weld, but the standard by-the-book repair method is completely off the table. So how do they fix the unfixable? How do they keep everything running safely? Well, let's dive in.
All right, to really get why some of these welds are considered unfixable, we first have to understand the standard fix. And that all starts with the incredible amount of stress that this simple act of welding puts on metal.
You see, when you weld something, you're creating this super intense tiny little inferno that melts metal, and then it cools down, fast. The problem is, this whole process of extreme heating and cooling is really uneven, and it leaves behind this hidden tension locked deep inside the material. Engineers have a name for it: residual stress.
And that coiled spring analogy? It is perfect, because this isn't just some passive state, it's stored energy, literally a spring that's trying to uncoil itself. And that release of energy can start as a tiny, microscopic crack that, over time, can grow into a catastrophic failure. It's a huge deal. So, in a perfect world, engineers have this brilliant solution to get rid of that coiled spring. It's called post-weld heat treatment, or PWHT. The idea is pretty straightforward. You take the whole component that you just welded, you bring it up to a really specific, high temperature, let it soak, and then you cool it down very, very slowly. Honestly, you can just think of it like a high-temperature massage for the metal. All that controlled heating and slow cooling lets the internal structure of the steel just relax. The atoms rearrange, the trapped stress is released, and the material becomes tougher and way less likely to crack. It's the gold standard for a reason.
Okay, but what about our big question? What happens when that nice, relaxing, high-temperature massage is completely impossible? Because the real world is rarely a perfect world.
In the real world, things get messy. I mean, just imagine trying to heat treat a small section of a massive bridge. It's just not going to happen. Or what if the equipment you're fixing has delicate electronics or internal parts that would be fried by the heat? Maybe the vessel is full of a liquid you can't drain. And on top of all that, the cost of shutting down something like a power plant for a long heat treatment, we're talking millions of dollars.
So, when the textbook answer is off the table, engineers don't just guess. No way. They turn to a highly specific and rigorous playbook of alternatives.
And this, right here, is that playbook. These are official engineering codes, guides that have been developed and refined over decades. They lay out proven, safe alternatives for exactly these situations, for when the standard heat treatment is, and I'm quoting here, inadvisable or impractical.
Okay, don't even try to read this, just look at it. The point here is the sheer complexity. These aren't just a few friendly suggestions. Every single alternative is governed by this complex web of precise procedures, qualifications, and standards. This is incredibly serious, highly regulated engineering.
So what are these clever workarounds? Well, they involve all kinds of strategies, like applying heat before and during the weld to control how fast it cools. But two of the coolest techniques are called temper bead and controlled deposition welding. And what's so smart about them is that they use the welding process itself to heal the metal.
The whole concept behind temper bead welding is just genius. Instead of one big heat treatment at the end, the fix is built right into the repair process. So, a welder lays down the first layer of the weld. Then, the heat from applying the second layer acts as a perfect localized heat treatment on the layer right below it. Each new pass, each new layer, tempers and refines the one before it, relieving stress layer by layer without ever having to heat up the whole thing.
So here's the fundamental trade-off, right? Your standard heat treatment is fantastic for brand new parts. It gives you this nice, uniform stress relief across the whole thing, but it takes a ton of time and equipment. These alternative methods, on the other hand, are designed specifically for in-service repairs. They give you a targeted, localized fix. The catch? It demands incredible precision and highly skilled welders who can follow these complex steps to the letter. Okay, so you've just pulled off one of these super sophisticated repairs. How do you actually prove that the unfixable weld is now truly safe? You have to verify it rigorously.
It's a two-step knockout punch. First up is examination. This means using non-destructive methods like ultrasonic testing to look deep inside the metal of the new weld for any hidden flaws. Then comes testing, where you have to prove without a doubt that the repair meets the original strength requirements and is absolutely fit for service.
And that is the most important thing to take away from all of this. When you hear about these alternative repair methods, these are not shortcuts. They're not about cutting corners. They are about applying a different and often much more complex and skill-intensive engineering solution to a problem where the standard fix just won't work. This is what keeps our world running, safely and efficiently every single day.
It really makes you wonder, doesn't it? This is just one example of the incredible, often totally invisible problem-solving that's happening all the time to maintain the complex systems we all depend on. What other engineering feats are out there, quietly keeping everything safe and sound? Thanks for joining us.